a group of us came up with when I was in the final year of my PhD, and then it sort of continued when I joined Facebook's AI research team, right? So this is a massive collaboration spanning multiple institutes. So there are several scientists, engineers, managers at Facebook who are involved. Then there's Zach Ulysses and his students at CMU who are part of this. And then we've had several postdocs and interns from other institutes like NeurIPS and Stanford as well, who've been a part of this project. So everything that I present is work by the entire team and not just me. Cool. So the motivation here is obviously climate change. So here I'm showing a plot of the power generation in US in 2018. And if you look at the distribution here, it's clear that most of the energy is coming from sources like natural gas, coal, slightly lesser from nuclear, and very little from wind and hydroelectric, and solar isn't even in the picture, right? This is obviously not the most ideal distribution. We'd want to get to a situation where we are relying more and more on renewable energy, right? And if we look at this plot for one day's worth of energy demand in California, compared to the generation of wind and solar energy, this is what it looks like. So the blue sort of shaded region here shows what the demand is during the course of a day. And the green shaded region shows what the generation of wind and solar is. So obviously wind and solar energy generation is not as much as the demand. But even if we were to naively scale up how many wind or solar energy power plants we have, this is what the plot would look like, right? So during the day, like roughly from 7 or 8 a.m. all the way till the evening, like 6 to 7 p.m., when the sun's shining, there's excess generation. And then during the night, or the early hours of the morning, when the sun's not shining, there's excess demand that's unmet. And so this basically prevents us from relying almost entirely on wind and solar. Like till we have a way to transfer energy from times of peak generation to peak demand, we can't rely fully on wind and solar energy, and we'll need to have fossil fuel-based backup plants, right? And although I'm showing these stats only for California and US, the sort of distribution in most parts of the world looks fairly similar. There is a huge amount of reliance on like fossil fuel-based power plants. And now if we think of what are the technologies we can rely on to store renewable energy, right? So like, again, going back to this plot, the reason we need a way to store energy is so that we can transfer it from times of peak generation to peak demand. Then two main technologies come to mind: batteries and pumping water uphill. So batteries, you may have heard of Tesla investing a lot in lithium-ion batteries for their cars, for their home power supply units, and so on. But these don't scale too well, right? So for example, Tesla invests something in the order of $50 million for each 130 megawatt hour installation that they set up. But just if we are to think of scaling this to US sized grids, that's just not feasible. There's like US spends in the order of 11.5 million megawatt hours. So that like the math doesn't work out here, right? And if you think of pumping water uphill, for those of you unfamiliar with this, this is like a super simple technique where basically the idea is that we'll pump water up a hill and store it there, and then and that's our stored form of energy. So we are basically trading off kinetic for potential energy, and then whenever we need electricity, we will make that water flow down through a turbine down the hill, and we'll use that to generate electricity. So this is like a super primitive method, but it works fairly well. So it's very efficient, like 70 to 80% efficient. But of course, there's a requirement here that you need hills and plateaus to be able to do this. So like this is a very small percentage of the generation capacity of the United States. And so what are alternative approaches, right? So one set of reactions that have the potential to scale to country-sized or global-sized grids is to have reactions of this sort. For example, water splitting. So during the day, when there's excess electricity, we can split water into hydrogen and oxygen. We store the hydrogen, And then whenever we need energy, we can burn that hydrogen to convert it back to water, and that releases electricity. So we can use that. And so the stored form of energy here would be hydrogen that we can later use in fuel cells. And there are actually a large number of such reactions that we can use where we suck carbon dioxide or water from the atmosphere, store it in some hydrocarbon form, and then burn it at a later stage to convert it back to electricity. And if you think of where this sort of fits in the overall picture of what I'm talking about here, so if you start from the bottom left, there's some renewable energy source, like it can be solar or wind. One example of a class of reaction might be water splitting. So we suck water from the atmosphere, split it into hydrogen and oxygen, store the hydrogen, and then burn the hydrogen later in fuel cells to generate electricity. So that's one example. We can also use the hydrogen in methanation plants to generate methane that we can again later burn to generate electricity. So it's like an overall flow diagram of what I was referring to earlier. Now, the main sort of critical bit in these sort of reactions, like if these reactions were so easy, they would be happening at scale even now, right? So the main critical bit that's still missing for these sort of reactions to be feasible at scale is that we don't have good catalysts for these reactions. So just as a refresher, catalysts are materials that can be used to increase the rate of a chemical reaction without being consumed in the process. So we need catalysts that are economically feasible, that don't get consumed, and yeah, that scale well, right? So to give you an example of what this entire reaction looks like, we can see the anode side half reaction when we are water splitting, right? So I have a cartoon diagram here. So the H2O molecule sits on a catalyst surface. So platinum is the catalyst surface. The hydrogen atoms fly away, leaving behind the oxygen. And that's basically it. Like that's the half reaction that needs to happen. Now, platinum is a great catalyst for this sort of half reaction. Platinum is obviously very expensive. And the search for alternate catalysts that are less expensive than platinum is not super easy. So if you think of common catalyst examples that are used in the industry, there are things like iron or gold. But the issue with iron, for example, is that it binds too strong to these H2O molecules. And so it can prevent the hydrogen atoms in some cases from flying away. So if it's too strong, it's attracting these molecules too strongly, and that hinders the reaction. Now, if it's too weak, then it might not even bind the oxygen atoms in the first place. So that's not ideal as well. So it has to be just right. Yeah, and platinum is a great catalyst for this reaction. It's not economically feasible, so there's a need to find alternate catalysts for this. And the way sort of chemists analyze these sort of reaction rates is through something called a volcano plot. And this is just to give an example of what that looks like. So on the vertical axis here, I'm plotting speed of reaction. And on the horizontal axis, there's attraction to the surface. And so as you increase the attraction to the surface, the catalyst surface, at some point, the speed of the reaction is optimal in this for this particular reaction to happen. And then if it gets stronger beyond that point, then the speed of the reaction drops, right? So going left to right, platinum is sort of sitting at the top of this volcano plot. And then if the attraction to the surface increases beyond that for other catalyst choices, then the speed of the reaction takes a hit. So we want to find alternate electrocatalysts that are near the peak of this volcano plot, right? But are much cheaper than platinum, ideally. One other term that you'll need to know about that I'll refer back to later in the presentation is something called a relaxation. So here, again, I'm showing a similar cartoon diagram as before, where there's a catalyst surface. So the blue and gray atoms are the catalyst surface. And then there's something called an adsorbate molecule. So in the previous example, the adsorbate molecule was a molecule of water, but it can be anything else. In this example, it's CO, so carbon monoxide. And the adsorbate molecule is sitting on the catalyst surface. So that's where it binds, and that's where the reaction happens, right? And so what I'm referring to with the relaxation is when the adsorbate molecule sits on the catalyst surface, it's initially in a high energy state. Now all of these atoms now exert forces on each other and move around till eventually the adsorbate molecule is in a configuration where it's experiencing zero net forces, so it's in a relaxed state, and that's the lowest energy state. So whenever we conduct chemical reactions in a lab, reactions happen at the lowest energy state. Like it'll automatically move around such that it's in the lowest energy relaxed state, and that's where the reaction happens. And this low energy state can be used to determine the reaction rate. Like if the energy of the relaxed state is low, then that means that the reaction will happen faster. It's much more feasible. You need to pump in lesser energy from the external environment for the reaction to happen. And this entire process of going from an initial state to a relaxed state via these intermediate steps where the atoms exert forces on each other is called a relaxation. So we say, yeah, we refer to the lowest energy state as a relaxed state. And here, although I'm like so far I've just been referring to one example. If you think of what are the space of catalysts or adsorbates that we might need to try out till we find something that works well, there are actually billions of adsorbate catalyst combinations, right? So each catalyst can be either a single metal surface, it can be 2 metals, 3 metals, any compositions of metals. Then you can also have some amount of dopants in those metals. So the space is really, really huge. And then if we think of what all chemical reactions we want these catalysts to be good for, then the space blows up even more. So there are billions of adsorbate catalyst combinations that we might want to try. And one method that I'm not going to go into detail of, something called density functional theory, that's a really accurate way of simulating what will happen in a chemical reaction without actually doing the reaction in a lab. It takes about 8 hours to simulate one combination. So like 8 hours times billions of combinations is a lot of time. So like we can't rely on that sort of method. So the idea here would be that we'll need some sort of machine learning method that can reduce this 8-hour time to a matter of a few seconds, so that we can see through these billions of combinations quickly. Any questions so far before I move on? I understand that a lot of these concepts might be new for many of you. So yeah, feel free to ask me any questions, because that'll just make the rest of the presentation much clearer for you.
Subriti, you're on mute, and I think someone has raised their hands to ask questions.
Cool.
Right.
Radhika.
Yeah, Radhika, we'll.
Yep, you can
Radhika,
unmute
should be
and
able to speak.
yeah.
What exactly the density functional theory?
Density functional theory is it's basically modeling the wave function for the electrons in each atom, and then it's trying to compute what is going to be the interaction between the different electrons of different atoms in order to very, very accurately predict what will happen in a reaction. So all of this is in simulation. Like none of these reactions are actually happening in a lab, like in a wet lab with like actual reagents. These are all simulation methods, but DFT is like a very, very accurate simulation method that can very accurately predict what the outcome of a reaction will be, but it's time consuming. And it relies internally on like modeling the wave function of each electron in each atom.
Is it like energy? Is it like energy calculation?
Yeah, so it's basically computing the energy and force.
Summation of energy among the electrons movement and the how much of the energy that can be stored at the end of that reaction, or what it exactly gives me.
Yeah, it basically computes the energy of the entire system. So the energy required to put together the entire system and the force on each atom. So what is the force experienced by each atom?
Okay.
Yeah, and that's essentially what we're. I'm going to go into details of it later, but that's essentially what we're trying to approximate with machine learning as well. We want to be able to compute the energy of the entire system. What is the, like, if it's a good catalyst, then the energy required should be low. And we want to compute what the force on each atom is going to be so that we can accurately predict how these atoms are going to move around.
Yeah. Generally, the catalyst will lower the activation energy of any reaction. So in that mode,
exactly.
Yeah, in that mode, you have to look into a good catalyst for the to take that particular reaction having a low activation energy.
Yep, exactly.
Yeah. Okay. Carry on. Thank you.
Thank you. Yep, thank you. I think we have another question on the chat by Kritika. So it says, are there certain kinds of architectures which are more suited to modeling these functions than others? And do they vary from atom to atom? I think you can access the chat as well if you'd like to read it up again.
Yeah, so I'm going to go into more details of it just in the next few slides. Yeah.
Okay.
I had a question actually. So what softwares are used to do the density function theory calculations professionally?
Yeah, so we use something called this software called VASP. It's not open source. It's a private license software. Like I think this research institute in Germany maintains it. I forget which institute. But there's also open source variants available, something called Quantum Espresso. That is quite popular. So VASP and Quantum Espresso are, I think, the two most popular packages that people use. No other sort of software comes to mind right now.
Okay, thank you.
Right, I don't think we have any more questions. I think we can move on with the slides.
Okay, sounds good. Cool. Yeah, so like I was saying, we need a way to approximate DFT, and one class of machine learning models that work, that sort of naturally are good for molecular systems are graph neural networks, right? So essentially what we're going to do is we're going to take each of these systems, we're going to treat the atoms as nodes, we're going to have edges between neighboring atoms. So if there are other atoms that are within a particular radius of each atom, then we're going to add an edge between them, and that's going to be our graph. So graph neural network operates on graphs, and this is how we construct the graph, right? Now for each atom, we're going to have the positions and the atomic numbers as inputs, and the outputs that our neural network will be trained to predict will be the forces. So the force experienced by each atom. And so here's sort of an example of what our systems might look like. So like I've shown you several figures of earlier as well, there's a catalyst surface. So those are the gray and the yellow atoms. I'll get into what the distinction is, why they are colored differently. And then there's an adsorbate molecule that's sitting on the catalyst surface. Now, in the course of a reaction, sorry, before I move on, so here I'm showing just a tiny slice of a catalyst slab and the adsorbate molecule, but we can assume it to be infinitely repeating in all directions because in a real reaction, there won't just be like 20 atoms, right? They'll be in the order of a few thousand atoms at the very minimum. Now, in the catalyst slab, the top two layers, or the top 2 or 3 layers, are known as free atoms because they do move around in the course of a reaction, whereas the bottom layers are just fixed in place. Like they, on average, the net force that they experience is 0 just because they're large and they're below the top few layers, so they don't have that many degrees of freedom, and so they don't move around at all. So like we refer to them as fixed atoms. So essentially, we are trying to model what is the force experienced by each atom in the top few layers. So the free catalyst atoms as well as the adsorbate atoms. When we say that there's an edge between neighboring atoms, this is how we compute that. So if we consider the red atom, we'll draw a cutoff, a circle of cutoff radius around it, and then whatever atoms are within that radius, we draw edges between them, right? So here's sort of another example of what that might look like for a catalyst atom that's in the second layer of the slab. And overall, what we're trying to do here is that we go from this structure to a graph. We feed that graph in to a neural network, and we predict the force on each atom, right? And then we'll do it again and again. Like we predict the force, we move the atoms around proportional to that force, just using classic Newtonian physics. And then we estimate the forces again. We do this whole thing again, and we repeat it till the force on each atom is close to 0, because that's when the atoms stop moving around, and we say that this is the relaxed state that the machine learning model has predicted, right? And ideally, if the graph neural network is able to do this well, then it'll be able to simulate DFT, but be way faster. And so that's the idea. And so this is what we refer to as the initial structure to relaxed structure task in our paper. And in terms of metrics, the kind of metrics that we track while we do this modeling is the force mean absolute error. So at every step, the neural network is predicting the force on each atom, and we're trying to measure what is the error between the predicted and the true forces. And for this relaxation trajectory overall, given the final relaxed state that the machine learning model predicts, what is the distance within a threshold of the true relaxed state? So we take the relaxed state predicted by the model, we take the true relaxed state, and we measure what is the distance between each pair of atoms. And we can also do a DFT calculation at the relaxed state that the machine learning model predicts and see if the true DFT forces at that relaxed state are 0 or not, right? Because the machine learning model might predict that the forces at that relaxed state are 0, but the true forces might still not be 0. So like one of our metrics that we track are that metric actually does a DFT calculation just for one step at the very end and checks if the forces are 0 or not. And this overall, if it works well, has the potential to reduce the time needed to simulate each reaction from 8 hours, which is what DFT takes, to the order of a few seconds, right? Because neural networks are typically very, very fast. So to start studying this problem, over the course of the last year and a half, we've collected a very, very large scale data set. So this is, to our knowledge, the largest data set of this kind that exists in the community, specifically for catalysis. So this has 1.3 million relaxations, both for training and evaluation. And if you think of different steps in a relaxation trajectory, then that in total amounts to more than 130 million training examples. So this is a fairly large data set. It has a diverse sampling of different catalyst compositions, different adsorbates. And yeah, so this is actually a good data set that we've put out there that the community can use to train and evaluate models, right? Cool. So I'm now going to jump into more details on the models. So as a reminder again, the inputs are the 3D atomic positions and numbers of each atom, and what we're trying to predict are the forces on each atom, right? Now there are two classes of models that we work with. So even with graph neural networks, we can do this force estimation in two ways. we call them force-centric versus energy-centric. So force-centric methods are just graph neural networks that are trained to predict a force on each atom directly. So we feed it a structure, it predicts the force on each atom, right? Energy-centric models don't predict the force directly. So we feed it the structure, and the model predicts the energy of the entire structure. And then we can compute the derivative of the negative gradient of that energy with respect to the atomic positions to compute forces. So if you remember from your initial physics classes, the negative gradient of the potential energy with respect to the atomic positions equals the forces. And so the advantage of doing it, the advantage of doing it this way is that it is energy conserving, in the sense that if we go from this is an example of like an energy landscape for different atomic configurations. And if we go from point A to point B to point C, the forces will sum up to zero. And that's the intuition that these energy-centric models are trying to capture, right? And in terms of a neural network, this is what it might look like. That we feed in the 3D positions, we do a forward pass, we get the energy, we do a backprop of the energy gradient with respect to the atomic positions, and we get the force on each atom, right? And because DFT gives us the targets for both energy and forces, we can have losses on both of those that we backpropagate through the model as we train it, right? So here's what a super simple model for a super simple energy-centric model for doing this might look like. So this one's called Chenet. It came out a few years back by Schutt et al. And it's very fast. It's not super accurate, but it hopefully gives you the intuition of how graph neural networks work, right? So the energy of the entire system is being predicted as the sum of the energies from each atom, right? So that's the summation sign. The F here is the neural network. So we might have some function that operates on each atom embedding. So each atom's hidden state. And the K here refers to that we might do this computation multiple times. So we might do several steps of this computation before we sum up the energies of all atoms to get the overall energy of the system, right? Now the atom embeddings themselves are not enough, right? So we need some form of interaction between different pairs of atoms, and that's what the message passing step does. So here, HS refers to the embedding of a source atom. HT refers to the embedding of a target atom. And what we're doing is we're doing some computation. The graph neural network is doing some computation to predict a message that goes from S to T. And then HT's updated embedding, so HTK plus 1 here, will just be the older embedding plus the sum of all incoming messages. And these messages are essentially vectors that are coming in from all neighboring atoms within a cutoff radius, right? And so the diagram here is showing what the different layers in the neural network might be. So E is just an embedding of the pair of atoms. So it might have something like the distance between those atoms, the atomic number embedding for each of those atoms. We pass that through a fully connected layer, so that's FC. We also pass the distance through a basis representation. So what I mean by that is that feeding in so let's say we compute the distance between two atoms, S and T. Feeding in that distance directly into the network doesn't work too well. So feeding in the distance directly might be like feeding in one scalar into the model, and that doesn't work very well. So instead of that, what we do is we have this sort of basis representation that discretizes the distance into a variable number of bins, and feeding that in and passing that through a fully connected layer works much better. And so that's the basic idea. So we compute this representation based on the distance between atoms. We combine that with the source atom embedding, and we get MST. So that's the message that's passed from S to D. Now, different papers use different sort of embeddings or different sort of basis functions for discretizing that distance. So one way you can think of discretizing that distance is that you have different bins, like is the distance between 0.1 to 0.2 angstrom, or is the distance between 0.2 to 0.3 angstrom? So you have, let's say, 100 different bins. You have zeros everywhere and a value of 1 whichever bin the distance falls in. And that would be something called a discrete filter. And I'm showing an example of what that might look like here for one particular molecule. And that also doesn't work too well. It also has optimization issues because this is like a one hot vector, which is 0 everywhere and 1 only at one place. So instead, what works slightly better is a continuous filter, where instead of binning the distance into these 100 bins or something, what we can do is we can have different thresholds. So a threshold of 0.1, 0.2, 0.3, 0.4, and we can, and each bin can store what is the distance of what is the difference between the true distance and that particular threshold, right? So this is sort of a softer embedding or a softer basis function that works quite well. And these people refer to that as a continuous filter, right? So the idea of continuous filters, it is pretty common, starting from this paper to a lot of more recent graph neural network papers that operate on molecular systems. And here I'm just showing an example of what these different basis functions might look like. One thing to note here is that like all of these are radially symmetric. So they're just capturing distance. There's no notion of angles. And that's why at whichever angle you draw, these are all radially symmetric. These are all fairly circular. And so papers that came after this also take into account angles, and like that becomes really important for capturing the true geometry of these structures, and that helps performance a lot. And if you look at the basis functions that these angles learn, that incorporating these angles tend to learn, then the learned filters on the right here are not radially symmetric. They're capturing distance as well as angular information. Right? So here, for example, I think these filters, if you look at column 3 or 4 specifically, these filters are for benzene rings. And so you will see symmetry along 120 degrees axis as you circle through these atoms. So it is really capturing radial as well as angular information, right? But of course, the issue here is that if we only take distance into account, we have to care about pairs of atoms. But if we have to compute angles, then we need 3 atoms, because we need 3 atoms to draw 2 lines that we can compute angle between. So this scales much too poorly. This is much more computationally expensive, right? Yeah, this is just a figure from the DimeNet paper. I'm not going to go into details of this. Let's look at some results. So you can ignore the ForceNet results here. ForceNet is an approach that we recently did that's much faster. It's force-centric, but yeah, we can ignore that for this discussion. So like I was saying, the DimeNet paper takes into account angles, but is much more expensive. It is a much more expressive function, so it works better, but it is much more expensive than Shinet that just takes into account distances, right? So the largest DimeNet model that we've trained thus far has 11 million parameters, and it takes in the order of like 1,600 GPU days of training time. Compare that to, for example, 200 days. And so these numbers might seem like obscenely huge to be able to like even think of experimenting with these models on. But these numbers are coming from the largest split of our training data set, which is 134 million structures. So if you were to experiment this in like a school lab setting, I would strongly recommend working with, so we do have smaller splits of the data set as well, with like 200,000 or 2 million structures, and those would be much easier to experiment with than this 134 million training split. Okay, this might be a good point to do another break for maybe questions. Any questions so far?
Sure. I had one thing in mind that I wanted to discuss with you. You talked about training the machine learning models, right? Since there's no accurate, like there's no way of manually doing the calculations. So what comment would you like to make on the accuracy of the models, since there's no way to figure it out manually and then compare the results? So what would you like to say on that?
It's so the whole DFT thing that I talked about, yes, that is expensive, but it is fairly accurate. Like like the energies and forces that DFT computes are very accurate. And the Open Catalyst dataset that I talked about, we actually did DFT calculations to generate that dataset, and that dataset is now publicly available. So that's the dataset we are training on, and so those numbers are fairly accurate, like to use as supervision for training your models.
Okay, so the machine learning models are actually learning stuff from the manual calculations that you've done before, and then you're using them. All right, makes sense.
Yeah.
We actually had another question that someone asked. Are we feeding these 3D positions as like a fully connected layer in this neural network, or is it in the form of a matrix or an image that we're feeding it in?
So it's not as an image. So what comes to mind when I think of an image is like a grid of like fixed dimensions, but that's not how molecules are laid out, right? These atoms might be in different positions in 3D space. So it's not an image. We are using these positions either to directly feed them in. So like if you think of each atom, they have XYZ coordinates. We can have a fully connected layer that goes from 3 to whatever, like 100, 200, 500. And that can be one way to do it. Another way to do it is where we don't feed in positions directly at all. We just use it to compute the distance between pairs of atoms, right? Or the angles between triplets of atoms, instead of feeding the positions directly. So like different papers do it differently, different approaches do it differently. But yeah, those are two ideas.
Right. Another question that we had was that what evaluation metrics did we use over here? Like, did we stick to accuracy, or like, is there any better evaluation metric in order to check whether, because we can't do it manually, like we had stated, like DFT doing it all manually would take a very long time to do. So what evaluation metric are we using in order to check whether we have the correct atomic interactions, as in we have the correct atomic interactions?
Yeah. So I talked a bit about that here. So we do have like the Open Catalyst dataset that I talked about. When I say relaxations, I should probably here say DFT. Like we did DFT relaxations to generate this dataset, right? And this is the dataset that we're using to for training and evaluation. So when we train these models, we track this metric called force MAE, so force mean absolute error. And that error is being computed between the predicted forces and the true forces that are coming from DFT. So that's one of the metrics that we can track for estimating forces. And another critical metric, so that's one critical metric. You can ignore distance within threshold, but another important metric that we track is called forces below threshold. And so the way that works is that we'll use this neural network to predict forces and update positions. We'll basically do this cycle again and again till the neural network finally predicts what the relaxed structure is. And then we'll actually do a DFT calculation on that predicted relaxed structure to estimate the force on each atom. And this metric is high only if the DFT computed forces on the ML predicted relaxed structure is very close to zero. I know it can be slightly confusing, but hopefully that makes sense. So we actually do a manual calculation here to see if the forces for the predicted structure are zero or not.
Right. That makes sense. Yeah. All right.
Yeah.
Are there any other questions? If the attendees would like to raise their hands, we'll unmute them.
Yeah, one question. After doing the calculations of the DFT model, whatever you got, and you have simulate, and you are getting some data of using these neural networks or machine learning, and then is there any error you find, or is that exactly matching? How much it will, how much it will be accurate enough, and is there any error also sometimes you may get?
Oh yeah, for sure. Our neural networks aren't modeling this perfectly, for sure. I am going to dive into results in the next few slides, so you'll get a sense for what these errors look like.
Okay. We had another question. So Kritika is asking whether you had earlier mentioned a comparison of the time taken by DFT versus that taken by an ML model, but is there an overall estimate as to how much energy these models could save when deployed in the industry instead of directly using the calculations made by DFT, like say it on a yearly basis?
I think that's a great question. And that's what it basically comes down to, right? Like, what is the difference in the overall energy that these neural networks can make? It is tricky to compute, though. So the way the workflow works is that we take these neural networks to make predictions on different catalysts. And then if we find a promising catalyst, we will synthesize that in a lab to see if it actually works well in the real world or not. Like all of this neural network and DFT, all of this is in simulation, right? We need to finally actually synthesize that catalyst in a lab to see if it works well. And now the energy difference calculation, or like how much energy savings we can have, will come down to that stage. Like how much better is that discovered catalyst than existing catalyst? So in the water splitting example, that would be a comparison to platinum, for example. Like how much savings is that discovered catalyst leading to compared to platinum? Just in terms of how much compute time these neural networks are saving, going from in the order of 8 to 10 hours to a few seconds. The bigger gain, I would say, is in that there are certain catalysts that we wouldn't even be able to try without neural networks, just because they're too expensive to do these calculations on, right? So neural networks are even outside of the efficiency gains are enabling us to even try thinking of evaluating certain catalyst compositions. So I think that's a huge win. We can now at least think of trying out these billions of adsorbate catalyst combinations that we wouldn't even imagine earlier, right? So I think the potential there is huge, but the actual energy difference, I think, is yet to be seen, till we find some good catalyst that actually works well.
I think that makes sense. Is there any other question?
Surface of the catalyst is more on the upper layer when compared to the lower layer.
Yeah.
In that scenario, how could you able to make use of complete catalyst for better energy driven reaction? Is there any of
Sorry, could you say your question again? I heard the first sentence, but I didn't really follow yeah.
The upper layer, you have said that it is very enhancing surface area, thereby the adsorbent can able to interact and have a force with the other atoms in the catalyst. At the lower level, lower layers haven't that much attractive surface area for the adsorbents. So in that scenario, how could you able to drive the total energy for the reaction to be commences in a short span of time to conserve the energy or to lower the energy for the reaction to be complete?
I feel like I still don't think I completely understood the question, but I can try to clarify it a bit. So yes, I showed a distinction between the upper layers and the lower layers, but when we actually do this reaction in a lab, it will always have those layers. It's not like we can get rid of the lower layers to maximize the surface area where the reaction happens, just because even the thinnest slice of a catalyst is thick enough to have both free and fixed atoms, right? The energy of the overall system is largely coming from okay, so what do I mean by the energy of the system, right? The energy that's needed to put together this system of the catalyst and the adsorbate. So if you have the catalyst in isolation, or if you have the adsorbate in isolation, that requires some energy. And then when you bring these two together, that requires slightly more energy. And so what I mean by the energy is just bringing together this entire system. Now that's there are multiple factors that come into play, but that's largely dominated by the interaction forces between the adsorbate and the catalyst, as opposed to the individual surface or free atoms or anything of that sort. So like the we could have a catalyst surface that's 1 micrometer thick or 5 micrometer thick. That isn't going to affect the energy of the system overall. Like it's largely going to be dominated by the interaction with between the adsorbate and the catalyst. Does that sort of answer the question? I don't think I fully followed it, but hopefully that helps.
Okay, we'll move on.
All right. I don't think there is any other questions. I think we can continue with the slides.
Sounds good. Yeah, so I just have some results that I can talk about. Yeah, so like I mentioned, one of the metrics we track is force MAE. So force mean absolute error, which measures the error between the true forces and the predicted forces. Lower is better, obviously. And so if you look at Chenet here, that's the gray line on the left plot. It's not very accurate, but it's fast. So like it's pretty good on the training GPU days axis, right? And then if you look at the DimeNet++ models, they're way more expensive in terms of training time, but they're way more accurate as well. So their force MAs are in the 0.028 range, right? And ForceNet, yeah, I didn't talk about the architecture at all, but just in terms of numbers, it is more efficient and it gets to almost the same accuracies as DimeNet++. So it's a good alternative to have. Yeah, just the same numbers in sort of a tabular format. DimeNet++ large that gets a force MAE of close to 0.028. And then we also have force MAEs on these other subsplits of the dataset. So out of distribution adsorbate, which means that adsorbates that were not seen during training, out of distribution catalysts, which means catalysts that were not seen during training, and out of distribution both. So both the catalyst composition and the adsorbate were not seen during training. So understandably so, the errors on those out of distribution splits are worse than the in distribution split, but not by much. Like especially if you look at out of distribution adsorbate and out of distribution catalyst for DimeNet++, that's 0.0318 and 0.0315. So they're not all that much worse than the in distribution errors. If our machine learning models were doing this perfectly, this MAE would be 0. Right? We can skip this. We can skip this. This is, yeah, so like I talked about this earlier as well, but this is sort of the most important, like if you have to take away one thing from this presentation of what we're trying to do, this is, I think, the most important slide. Basically, what we want to do with our machine learning model is that we'll place the molecule near the catalyst, and then we want to find the atomic positions with the lowest energy, right? And the way we do this, just to reiterate, is that for each atom, we'll predict forces, we'll move the atoms around based on these predicted forces, and we'll repeat this till the force on each atom is close to 0, right? Here are a few sort of qualitative examples of what these predictions look like. So the initial and relaxed states, the first 2 rows, are from DFT. Yeah, the differences are sometimes hard to see, but if you look at the first column, for example, you can clearly see that the adsorbate is in a slightly different configuration between the initial and relaxed state. And then I'm showing the relaxed state predictions from Chenet and DimeNet++. And if you look at the DimeNet++ row, the percentage value basically measures how close is the predicted relaxed state from the true relaxed state. So the rows to compare here would be row 2 and row 4. And so the DimeNet++ in predictions in a lot of cases, especially for like column 1 and column 3, column 4 as well, they are pretty close to what the true relaxed state is. It's obviously not perfect. So on column 2, for example, it does a very poor job. The configuration looks very different from what the true relaxed state is. but it does well on some systems. So it is promising. Cool. Yeah, we have a website, opencatalystproject.org. All of our papers, data, code, leaderboard, discussion board, everything's available there. So I encourage all of you to check that out. Yeah, on the website, you'll find a link to our code repository that should be pretty straightforward to use in case any of you are curious. We have all of the different configurations for these models on different dataset sizes that you can check out. The code base supports several models, so GemNet, CGCNN, DimeNet, SHNet, ForceNet. It has several models, and it has a lot of helper scripts for sort of setting up the data, making predictions, submitting the results to the evaluation server, and so on. Right? Yeah, just to sort of give a hint of what these config parameters might look like, we've tried to make this as easy to use as possible. So this is an example config for training on the 2 million dataset. So this is the SHNet model. We can define what these different hidden channels, what the size of the model might look like. We can define different optimization parameters. So which optimizer to use, what is the learning rate scheduler, what is the energy loss coefficient, what is the force loss coefficient, that sort of a thing. And yeah, once you define this in the config, you can kick off a training job. It's as simple as that. So zooming out, what is sort of the overarching goal of the project? Like in this presentation, I mostly talked about creating this data set and training models, right? Once we have models that work well enough, we're going to run inference or like make predictions on the billions of adsorbate catalyst combinations. So that's the brute force inference step. That's the next step. When we make predictions at such a large scale, we obviously would want to know whether our predictions are correct or not. So for some subset of that of those billions of combinations, we'll do DFT verification. So we'll take those predictions, we'll run DFT calculations, and see if our models do a good job of predicting relaxed structures or not. We'll then repeat this till we have models that are good enough, right? Like we'll keep iterating on this till we have models that are good enough. So we might have to generate a new data set if we find examples that our models are poor on, right? Now, once we have models that are good enough, we're going to move towards experimental verification. So what I mean by this is that we'll take some predictions from our machine learning models. We'll we'll collaborate with a chemistry lab to actually synthesize these in a lab setting in the real world, just to see if our models are making good predictions or not. Like all of this is in simulation, right? Everything on the left-hand side. So the experimental verification step is actually very, very important to see if our models' predictions are good or not in the real world, right? And alongside all of this, we're going to like open source all of our tools, data sets, code, everything. We've already done a lot of that. All our code's on GitHub. The data set is public. And hopefully, if we do all of this for long enough, we can make the Earth happier. So that's the idea. Yeah, and just to give a sense for like two ongoing directions in the team, we think of the split along two axes, the horizontal and the vertical. So the horizontal, what I mean by the horizontal is that there's a fundamental simulation problem that we are trying to address, which is ML models for DFT approximation. That has applications beyond just catalysis. Like if we can develop a graph neural network that does that well, we can use that not just for this particular project, but for a whole range of projects. And so that's the horizontal that we're working on. And then the vertical, what I mean by that is the end-to-end pipeline for a specific class of reactions. So going from training models in simulation to making predictions to actually synthesizing discovered catalysts in a lab, that would be the vertical step, right? And so there's effort in the lab along both axes. So in the horizontal axis, the kind of things we are looking at are how can we scale up these graph neural networks. So instead of like tens of millions of parameters, can we get to 1 billion parameters, and how well do those models work, right? We're thinking of like how can we bake in more chemistry knowledge, like so that these graph neural networks don't have to learn things from scratch. We're thinking of what can be different kinds of training data, and then we're looking at what can be self-supervised methods for training these models more efficiently. Right. In terms of the vertical axis, CO2 reduction reactions are sort of the current focus of our project, but other things that are of interest are for example, DFT and machine learning hybrid strategies. So instead of replacing DFT with machine learning completely, we can maybe think of a hybrid, right? Like we can take the relaxed structure that our machine learning model predicts, and then we can run DFT starting from that step. So it can still reduce the number of DFT calculations needed. So we're thinking of hybrid strategies there, and like a couple of other things. And that's it. All of our code data papers, like I said, they're all publicly available. I'll share these slides. You can check out these links if you want to read more about the project. But yeah, happy to take more questions.
Right. I think this is really amazing, sir. We did have a few questions, though. One of them was that I think you talked about bringing in a bit of chemical knowledge so that the GNNs don't have to train from scratch. Do you think we can use transfer learning over here in any sort, as in train our neural network using the transfer learning, as in have some predefined neural hidden units before we start computing the atomic interactions?
Yeah. So like I think we might be conflating two different concepts here. So transfer learning, when I think of that, is when basically we train on some initial data set, which is large, diverse, all of those things, and then we transfer that network to a different domain, right? Maybe that's what you meant by pre-training certain parts of this network, right? But what I meant by baking in chemistry knowledge is that instead of just relying on atomic numbers or atomic positions, we can use other knowledge here. Like what is the radius of each atom? Like different atoms have different radiuses, right? Which group or period does each element come from? Are there other element specific properties that we can use, right? Like how many electrons does each atom have? So instead of learning all of that from scratch from like a training data set, we can try and think of what could be ways to encode that information in the neural network. The transfer learning idea is interesting though. Like our data set is not in this particular context, but like the Open Catalyst data set is large enough that I can see applications where you take a pre-trained model on the Open Catalyst data set and you use it in some other molecular application where the data set might be very small. So that is definitely possible. We haven't explored that, but it's worth trying.
I think we have another question. So this is like, though we can innovate AI for designing smart solutions to combat climate change, but with recent development of big models like GPT-3, the overall carbon footprint of AI itself is huge. So what's your take on that? Is there any solution we can that we can reduce this carbon footprint in any way?
This is something that I wanted to ask you as well, because I'd read somewhere that one artificial intelligence model can, give out emissions which is equivalent to 5 times of an American car in its lifetime. So would you still go ahead and say that some things like this are doing more good than harming the environment? So what are your views on that?
I mean, yeah, like it would be my answer would be what you probably expect, right? Like it's not great. Like we need more efficient models that can reduce the carbon footprint. But if you think of like, yes, we might be emitting more CO2 equivalents right now by training these models at scale versus the potential future reductions if we discover something. That's the trade-off we are going for. There is at least that hope with this sort of a project that it can reduce potential future emissions. With GPT-3, there's not even that hope, right? Like it's a language application. So like, yeah.
Yes, sir. We did have a few more questions that, so we had actually put out a form before where people had asked some questions beforehand, before this session started. And So the first question was that in the futuristic aspects of AI and sustainability, do you think novel biotechnology projects could play a key role as well? If so, in what way do you see this happening?
Yeah. So I'm not a biotechnology person, but some applications that fascinate me in that domain are things. So there's a lot of research right now in detecting biomarkers. So what are biomarkers, right? Like if someone's going to have for diseases like, for example, cancer, right? It's not all that useful uh, if someone has cancer and then you detect it. Like, yes, it is important to detect it at that point, but what would be way more useful is if we can find biomarkers in the body that can detect the that in future, like 10 years later, this person might be having cancer, right? And biomarkers can be things like the levels of different enzymes or like different proteins in the body or how they're interacting with each other. It can be any sort of statistic that you might derive from different chemicals in the body. So there's a lot of research in trying to detect biomarkers for various diseases 10 to 20 years in advance. And that can be game changing. Like I feel like machine learning is pretty ripe for an application of that sort because that's what machine learning does, right? It can detect patterns in large data sets. And so people are looking at that. People are also looking at drug design, like protein. There's still a huge leap from like protein folding to actual drug design, but that's of course a very popular area as well. People are looking at biomarkers for aging-related diseases as well. That can be used machine learning to detect biomarkers for aging. So the entire biomarker space is something that I'm pretty like fascinated by. I don't obviously work on it. I haven't ever studied it. So I'm an outsider. But yeah, that's what comes to mind.
Right, of course. We did have a few questions that were a bit outside the technical preview and were more in generalized to research in. And would you be open to answering those questions for like a lot of people over here are budding researchers, and we would really like to hear your advice to undergraduate researchers and who are just starting out, basically.
Yeah, absolutely. But can we do like a 1 minute break? I would like to get like a glass of water because I've
Sure.
been talking for a while.
Course.
Yeah. So give me a minute. I'll be back.
Mhm. Supriti, there are a couple of more questions on the technical end, then we would start with.
Okay, cool. Yeah, let's go.
So we had a few. We actually had a technical question before we move on to the generalized research questions. So
Yep.
one of Kritika asks, are there any results pertaining to the difference between the models trained on the angular information versus those that were not? or even the other aspects that you mentioned that could be integrated into the initial embedding vector, such as the group of the atom, etc.?
For angular versus just distance, yes. Like, I can, yeah, the links are on my slides, but there's this paper called DimeNet that you can find on arXiv. That paper incorporates angular information, and it helps a lot. Like, it helps improve over just distance-based models by a lot. The reason for that is that these are basically molecular structures, right? And you want the neural network to accurately encode the geometry of these structures. And so just distances are not enough to accurately encode the geometry. You need the angular information between these different triplets of atoms. And so, yeah, like, check out the DimeNet paper that does a good job of showing improvements with angles. And there are papers that also incorporate more knowledge of these elements. And yeah, like, at varying levels of, I would say, like, computational expense. So there are some papers that will do some cheap DFT-like computation to generate an intermediate structure and then feed that into the neural network. But even though that DFT-like computation might be cheap, it might be in the order of like 30 minutes to an hour. So that's still overall adding to, like, it's still not in seconds to get a prediction, but there are papers of that sort as well. One that comes to mind is called PhysNet, so PhysNet, that does this. They actually have promising results, but there are other papers as well that do this.
Right. She also asks whether there are any other initiatives, like with Facebook and CMU, that are working on with respect to the intersection of AI and sustainability.
Not that I know of. I think this is the only project at least in the AI research team at Facebook that's focused on climate change. Of course, there are other things that Facebook overall does for sustainability, in the sense of, like, they're making sure their data centers are carbon neutral or like approaching carbon negativity. But in terms of climate change, or more like external breakthroughs, I think this is the only thing that comes to mind right now. But if you look at other orgs, like, for example, Microsoft or DeepMind, they also have efforts in climate change. So it's not, like, Facebook might not be doing it, but other big tech companies are doing it.
Regarding that only, which technological advancement in recent times would you say you think is the most promising one for a sustainable future? Something in recent times which you came across or are working on, maybe, which you think is something that will be.
Do you mean in, like, AI for climate change specifically?
In AI for climate change, or physical aspect of it as well? Anything that you come across?
In AI for climate change, I would say nothing. Like, I haven't seen any major breakthrough in the last several years. The reason for that is that there's not that many people working on it. Like, it's a new, there aren't, like, the biggest problems in climate change are mostly economic and policy related. Like, they're not necessarily tech problems. Yes, there are some tech problems, but maybe they're not the biggest ones, and that's why there aren't that many people in AI working on it. But outside of AI, like in the climate change space overall, in climate change tech, there are a lot of startups that have come up in the last few years who are trying out different carbon sequestration approaches. So, like, approaches to capture carbon from the atmosphere. Yeah. So that's exciting. I haven't seen any results that can be scaled to production level. These are, like, a bunch of people have initial results, yet to be piloted at scale, but at least people are working on it. So I think, that space is exciting.
Yeah, I think that is it from the technical end of things. So, Priti, you can go on with the experience.
Right. So we did have a few questions that were a bit general to research. And one of them, of course, was your advice. I think all of us over here would love to know your advice for undergraduate researchers who are still starting out, or probably those, like, what all research, how can we all proceed with research at an undergraduate stage?
Yeah. So AI, I think, is super competitive these days. It wasn't as competitive when I was starting out. So it helps to start early. I think as an undergraduate, the best way to make impact, get noticed, get research opportunities is probably through open source code, right? Like there are like so many papers open source code on GitHub right now, but there still are several papers that don't. And so you can do this in multiple ways where you implement an approach for a paper that hasn't open sourced their code, and you put out that implementation on GitHub. You maybe post on social media, try and get the right people to notice it. And yeah, like that can be a good way to get your work noticed, get your work sort of being used by other teams. If people are using your work that you've put out there, then you will get noticed. Like it's as simple as that. Another way to go about this could be that like for papers that are open sourcing code, you can take their code, you can try running it, you can try and find mistakes that their model makes, and then try and find how can you fix those mistakes. And maybe eventually it'll lead to something that you can write a paper about. Right? Even just running their code at your end will help build intuitions. So like, yeah, like don't ignore open source and GitHub. I think writing code, getting your code out there is a like a guaranteed way to get noticed. I think that's super important. In terms of research opportunities, I don't have a very good sense for how competitive or easy to get those are right now, especially at an undergraduate level. Like when I was in my undergrad, I wasn't into AI. Like I was doing research in other things. Like for example, in my third year, I did an internship that was on computational neuroscience. So there was a lab that I was working on that had this very tiny setup of like a zebrafish sitting in a jacuzzi, fixed in its place, and being shown different. Like there was a screen in front of the zebrafish. It was being shown movies of different kinds, which was basically like colors of different kinds. And the idea was that so we were using a zebrafish because the skin of a zebrafish is transparent. So as different neurons fire in its brain, you can actually see it in a microscope. So the idea was that you take stimuli, you show it different stimuli, so colors of different sorts, and see which neurons fire in its brain to develop a better understanding of how a zebrafish brain works. And I thought that was super interesting. It wasn't anything to do with AI, but that's how I started. So I think like it might it's very hard to know in your undergrad like what you eventually want to be doing. So I would say just explore. Like getting your foot in the door anyhow is kind of important, right? Like if you get a research opportunity somewhere which is not even in your direct area of interest, I think that's fine. Just do it. At least you'll learn how research works, how science works, even if it's not in a domain that you like, right? And then you can use that experience to like get opportunities later, right? Even if it's in a slightly different area. And that's what happened in my case, right? Like that particular project led to a paper, and then that advisor that I worked with, he was happy to write me a letter for like future opportunities, and that's how that led to one thing to another to a PhD, right? That's how I started out. Yeah, so getting your foot in the door anyhow, I feel like that's kind of important.
That's amazing. I think, yeah, the other question that we had was that, like, basically about this itself, that you started out with something else and then you went and did a PhD in computer science, I think. And after that, I think you worked on such diverse topics. You went from explainability to vision to reinforcement learning, and right now you're working for climate change. So, like, is it necessary at least in computer science, like you said, it's very competitive. So is it necessary to find a niche and start working on it, or do we is it all right to be a bit more diverse about the topics we choose and just go with the flow over here?
I think I have a huge amount of respect for people who know very early on what they want to do. I think it didn't come naturally to me. I think it's also very hard. Like, how can you have clarity to know what you want to be working on 10 years down the line? You're a different person 10 years down the line, right? So I think that's very hard. the way I went about it was that after my undergrad, before starting my PhD, I actually worked with my PhD advisor as like on an internship. So I did a 1-year-long internship with my PhD advisor, but I was just doing research in AI. So that was my first experience in AI. I had never worked on machine learning before that. And I had a really good time at that internship. Like whatever I was doing, I was having fun. I was enjoying it. I was reading a lot of papers. I didn't publish anything that paper and that year, and that was fine. But I was having fun, and so I was like, if this person, if so, my advisor is Dhruv Batra, if he's willing to take me on as a PhD student, I'd be willing to join. Like this sounds like fun. So like I had read all the stats of like PhDs on average take like 6 years or whatever in the US, but my approach wasn't necessarily to like going in. It was clear to me that I'm going to do this till I enjoy it. If I stop enjoying it, I'll quit my PhD, and that wasn't that big a deal in my mind. Like honestly, I knew that I will figure out some position in software that would pay me a decent salary to sustain myself, and I would be okay with that. And so like it going in, it was like I was certain that I don't necessarily need to come out of this with a PhD degree. I just need to be working on this till I enjoy it, and that was my thing. In terms of topics, I jumped around a lot. Like my PhD started with this problem called visual question answering, where I was working on building models that can answer questions about images, right? So I worked on that. I extended that to like a dialogue setting, and then I worked on some robotics-inspired applications like embodied question answering, where there's robots that can move around in a house-like environment and answer questions. And that was the main theme of my thesis. These VQA, visual dialogue, embodied question answering, that sort of thing. And then in my third or fourth year, I started thinking about, okay, what do I want to do after my PhD, right? Like, do I want to be working on these problems long term or not? And that's when I went out just searching with an open mind that like, okay, what are the biggest problems? And that's how climate change started seeming like okay, that this is likely the most important and urgent problem to be working on. And so what are applications of machine learning in that domain, right? And that's how this project started in the beginning of my fourth year of my PhD. And then I graduated, and then I joined FAIR, and FAIR was happy to let me continue working on it. So that's how this came about. But yeah, I have jumped around a lot in terms of topics. Even now, I feel like this particular project is like, it's not a kind of project that can be solved with like a 1-year effort. It is a long-term project. And so like I'm enjoying it right now. I learn things on a daily basis. I don't have a chemistry background, so like I'm learning things on the fly as I work on this. And I do see myself working on this for at least 3 to 4 more years. And then I might be doing something entirely different, depending on like where this project is, or depending on what I think of as important problems after that. So I think it's totally okay to like jump topics. Like that's not, you don't need to know upfront what you're going to be working on. Very long answer to your short question, but hopefully that helps.
Yeah. Along the same lines, I had a question. What exactly? This would sound cliched, but what exactly was your motivation to start working on climate change and sustainability? Or was it something that you got interested in just because you were in the field for AI and you wanted to do something new?
I was looking for something that could make impact in terms of like, okay, like what am I, like what do I know, like what is my expertise in versus what is the lever that I can pull to make the biggest impact on like humanity or people overall, right? And so there were a few different options. Like I could work in healthcare, AI for healthcare. There are a lot of startups that are doing that. I could work in self-driving, like cars that can drive themselves, right? There are a lot of startups that are doing that. And then the third thing that was on my mind was that climate change is more urgent and important than self-driving cars or like healthcare, at least in some settings. not with the pandemic. The pandemic is of course more important. But so that's how climate change came about. And so I was basically just out there searching for, okay, what should I work on to make the most impact? And that's how, yeah, I got interested. And to add to that, I think there was a startup time, right? Like I spent the first 6 to 8 months when I started thinking of climate change just reading, because like that was new to me. I'm not a climate change person. I wasn't a climate change person back then. So I was just reading different papers, talking to different people, trying to get a sense for what are the most important problems in this space. Are these problems even solvable? Can AI do anything to these problems? Because like there are lots of problems in climate change, right? Like this is not the renewable energy storage is not the only problem here, right? And so even that took a lot of time.
All right, makes sense. Is there anything else, Supriti?
Are there any questions from the audience? Anything you want Abhishek to address, or any of the questions that you have in mind?
I think Radhika has a question.
She raised her hand. Yeah. Yeah, I think she can unmute herself now. Yeah.
Did you find any solution for good catalyst now?
Not yet, but we are in the process of, so by the end of this year, so by I think December or maybe early next year, January, we are going to have our first set of catalysts that are predicted by our ML models. They will actually be synthesized in a lab to evaluate if they're good enough or not. So we are all, like the team mostly is working towards that. So those results will come in January or February. And that's, I think, super exciting. Like if you think of how hard this problem is, like making graph neural networks run on like billions of combinations, and then we obviously can't synthesize billions of combinations in a lab, right? So we have to bring it down to like 100 predictions at most that can be synthesized in a chemistry lab. Like so that's a hard problem. So like that's something that'll come in, I think, early next year. I think the first set of those results will, yeah, if I'm being honest here, the first set of those results will probably be a failure. Just because, like, yeah, this is the first time we're doing this. So like, but at least we'll have the pipeline set up to go from training to predictions to actually synthesizing things. And then it's just a matter of iterating on this again and again and again for the next year or two, till we actually find a catalyst that works well. Yeah.
Yep. I think that is it. All right. Thank you so much, Abhishek, for taking our time to talk to a bunch of undergrads about things that we won't fully understand right now. So we really appreciate it. I think
thank you for having me.
Yeah.
Wait, Radhika seems to be raising her hand. Was there another question?
Okay, we can ask. Just a second.
Do you have a tie-up with any chemistry lab people for validation?
Sorry, do we have a what?
Any tie-up with chemistry group, chemistry team for validating the catalyst for synthesis in their labs? Do you have any tie-up?
Yeah.
Oh.
Yeah. Like, so the folks at CMU, they're from the chemical engineering department. They are mostly computational chemists, though. So the CMU folks are one such group we work with, and then we also work with University of Toronto. That's sort of a collaboration that's coming up. That's not fully set in stone yet, but the University of Toronto folks, they are actual experimentalists. Like they don't do anything computer science related. So they are going to be synthesizing these materials for us. So yeah, we are working with a lot of people who have a background in chemistry.
Yeah, I think we're done with the session. Thank you so much for all of the knowledge that you've imparted us tonight. And thank you for taking out the time for it.
Absolutely. Yeah. Thank you for
Yeah.
having me, Supriti and Shresht. Yeah. Feel free to reach out to me on my email if you have any, if you or anybody in the audience has any follow-ups. I'll be happy to answer them. You already have my slides, so you can share that.
Okay.
Yeah.
Yeah.
I think this
All
talk
right.
was very intuitive and has given us a lot of insight into the field of AI and sustainability, like from covering the basics of the topic to explaining the current research that you're doing. The entire talk was very wholesome. So we all look very forward to having more of these interactions with you in the future. Though also we would like to thank such an enthusiastic audience for making this event successful. If the attendees, of course, have any more questions, like Abhishek just suggested, you can feel free to approach us after the event and we'll connect you with the speaker. And I think we would like to talk a bit about RSM to the attendees as well. So the Research Society MIT was formed with the main goal to promote the idea of research among students and connect them with professionals and experts from all around the world and help create a society of like-minded individuals passionate about research. So we host a range of events, webinars, alumni talk, and paper presentations. So if you would really like to attend them, please do follow us on Instagram and LinkedIn for updates. And you can check out our website for collaborations on ongoing projects as well. We have posted the links for the same on the meeting chat. We would also love to know any feedback or suggestions that you may have. So thank you so much, everyone, for coming today. And thank you so much, Abhishek. Have a very pleasant good night. Good morning for you.
Okay.
Awesome. Sounds good. Thank you. See you.
Okay. Bye.
Thank you.
All right. Thank you, everybody.